I'm graphing with quadric functions.
Quadratic? Okay.
Yes. So the first one, it says graph the function, and the parent graph is f of x equals x squared.
Okay.
So the first equation is p of x equals 7x squared.
Okay. I would so give to be a good artist. What does the parent function look like?
Well, b start with 0 would be the vertex.
Yeah, it's a parabola. Basically like that. Okay? So,
Okay.
that's that function. What's the consequences of the 7 in front of the x squared?
You have to multiply it.
It's called a vertical stretch factor.
Okay.
And basically what's going to happen is that if a point was right there on my parent function, it's going to be 7 times higher, right?
Right.
It's going to be up there. If a point is right there, that point's going to be 7 times higher. And what the effect of that is it steepens the parabola, makes it skinnier.
Okay.
If this number is greater than 1, it has the effect of, if this was a string and you pulled on this two ends of the string, it would look like the skinnier parabola. So if this vertical stretch factor is greater than 1, it makes it skinnier. If it's between 0 and 1, it makes it flatter. In other words, if I had x squared 1/2 x squared, that would look like this.
Okay.
Okay? So a number in front of the parent function is a vertical stretch or squeeze factor.
Okay.
Okay? What's the next one?
Well, it says graph.
Okay, I just did, and that was the dotted line.
I'm sorry, not graph. Make a table. My bad.
Oh, okay.
I'm so sorry.
No problem. Tables are relatively easy. X goes there. Y goes there. And just make up points for X and see what Y is.
Okay.
Well, when X is 0, Y is 0. When X is 1, what is Y?
Let's see. 7.
Yeah.
Wait, no,
I
7.
really should
Where?
call that P of X, I guess.
Okay.
Yeah, it's 7. When X
Okay.
is 2, what is Y?
14.
Well, we're going to square 2, which is 4, times 7, so it's 28.
Okay.
When X is 3, we're going to square 3, that's 9, so this is 63. Okay, so
Now,
I don't know how much of a table they wanted you to make, but you could make whatever length.
If it's a parabola, isn't like everything, like if it's a -1, would it still be 7?
Yes.
Okay.
And let's go ahead and put a -1 in there, and 7. And notice why that's true. In other words, no matter whether I'm to the right of the y-axis, where x is positive, or to the left of the y-axis, where x is negative, it gives you the same y value. In other words, let's call this point 2, which makes y 4. Okay? But in the P of X graph that looks like this, notice that when X is 2, Y is way up here at 28.
Okay.
But notice that when X is minus 2, it doesn't change the Y value. It's still 28. Because I take minus 2 and square it, it becomes positive 4. So even over here, when x is minus 2, y is 28.
Okay.
But you're right. The table, I should have included positive and negative numbers. I could have maybe started at minus 2, then minus 1, then 0, then 1, and then 2.
Okay. So you said it's a vertical stretch.
Mm-hmm.
So how can you tell by how much did it stretch?
By the factor of 7.
Okay.
What
So,
that essentially means is that wherever my point would have been on the parent function, notice that that point's at 4. Well, on this function, it's 7 times higher because it's being multiplied by 7, and that's why it's at 28.
Oh, okay.
So it's a vertical stretch by a factor of 7. Every single point that would have been on the original curve is now 7 times higher on the new curve.
Okay. Makes sense. Okay. The next one
Before I
is
erase anything, I don't want to erase the parent functions here.
yeah, parent functions.
Okay.
Okay. The next one is q of x equals 1/2 x squared. Now, if it's anything less than 1, isn't it a shrink?
Yes. Well, it's not quite fair to say less than 1 because negative numbers do altogether different. If the absolute value is less than 1, it's a shrink. So it has to be between 0 and 1 for it to be a shrink.
Okay.
Or between...
And if you're to say shrink, would it be a factor of 1/2?
Yes. So, and the way I know it is that this point that's at 4, well, it's now going to be a 2 because I'm multiplying it by 1/2, so the new point would be right there. Okay? And the effect of that shrink factor is to flatten out the parabola so that it goes through that point there. So that this point here is half of that point there. This point here is half of that point there, and so forth.
Okay.
So, and it's not, the reason it's not correct to say less than 1 is because if I have, say, a minus 2x squared, let's say I had a h of x that was equal to minus 2x squared. Well, minus 2 is less than 1, but this is not a shrink.
Because it passes
the absolute value of it is greater than 1.
Okay.
The consequence of the negative sign is it merely reflects it over the x-axis. So if I was going to graph this, it would first of all be reflected and then stretched. So it would look something like this. In other words, skinnier than the original parabola. Skinnier meaning that's being stretched, but it's being reflected first and then stretched.
Okay.
Okay. So the whole
isn't -2 isn't that the a value?
Yeah.
Okay.
But if we're talking in terms of translations and reflections, there's 6 things you can do to a function, to a parent function. You can move it up or down. That's a vertical shift. You'd get that by adding a number after the function. You can move it left or right, which is a horizontal shift. And you get that by x minus 3 quantity squared. In other words, if I add or subtract a number inside the parentheses, that is a horizontal shift, either left or right, depending on whether that sign on that number. Okay. Then you have the vertical stretch or squeeze. What was the other?
Or stretch or shrink.
Stretch or shrink, excuse me. And you get that by whatever the number is in front of the function. And
Okay.
finally, you have a horizontal stretch or squeeze. And you would get that by putting everything inside the parentheses. In other words, instead of like this, I'm going to put that whole 2x inside the parentheses before squaring it.
Okay.
This 2 now acts as a horizontal squeeze or stretch factor, but it works in the opposite way of the vertical one. In other words, if this number is greater than 1, it's a squeeze.
Okay.
If it's between 0 and 1, it's a horizontal stretch.
Okay.
Okay? And in cases like these parabolas where you're working with quadratics, horizontal squeezes look the same thing as vertical stretches. In other words, I'm saying that's a horizontal squeeze. Well, if I perform the math here, that's 4x squared. Well, that's the same as a vertical stretch by a factor of 4.
Okay.
And that's what would happen if I take this parabola and try to squeeze it together by applying pressure from both sides, and I do it by a factor of 2, this 2 right here, it ends up being identical to a vertical stretch by a factor of 4.
Okay.
So those are 4 things you can do, and the other 2 are reflect about the x-axis, and you do that by putting a minus sign in front, and you reflect about the y-axis by putting the minus sign in front of the x.
Okay.
So those are the 6 things you can do. Vertical stretch, vertical shift, horizontal stretch, horizontal shift, reflection about x, reflection about y.
Okay.
Only those 6 is all you have to worry about with these. And you'll notice that with quadratics, a reflection about y doesn't change it at all. In other words, if there's my parent function, f of x equals x squared, and I said, well, f of minus x would represent a reflection about the y-axis, well, that's minus x quantity squared, which is the same as x squared. So when I reflect this curve about the y-axis, it doesn't look any different. It looks exactly the same. It's symmetrical about the y-axis.
Okay.
So sometimes a shift or a reflection about the y-axis does not change the look of the graph at all.
Mm-hmm.
Now, if we were talking about a parabola that was over here, and I shifted it or reflected it over the y-axis, then it would look like this. So it kind of depends on where it is. But if it's symmetrical with the y-axis, then reflecting it about the y-axis isn't going to make it look any different.
Okay.
What else?
Okay, the next one is g of x equals negative 3/4 x squared.
Okay? Always do your reflections first, and it does matter.
Because can you end up like on the wrong?
Well, it doesn't matter in this function, whether you do it first or second, but there's a lot of times where it will matter. Just remember that as a general course, always do your reflections first. Doesn't matter which reflection you do first. And sometimes there's multiple reflections. In other words, if I said my parent function was e to the x, you familiar with that function?
No.
No, never heard of that one? Okay. I could do two reflections. Minus e to the minus x is a reflection over both the x-axis and the y-axis.
Okay.
This minus sign causes it to reflect over the y-axis. This minus sign is a reflection over the x-axis. So more complicated functions, some of these things make a difference. If you're dealing with quadratics, then they don't always make it look different. Okay, so we only have two things going on here. We got the minus sign, and we got the 3/4.
Okay. So the negative would flip.
Okay, so we'll do it 2 steps at a time. We'll do the first step, which is merely a flip.
Okay.
Perfectly symmetrical flip.
So
now, is this going to be flatter or steeper?
Be flatter.
Skinnier or fatter? Flatter by
factor of 3/4.
Well, not by. It's not quite say flatter by 3/4. It's 3/4 left. The way to think about this is any point that would have been there is 3/4 closer to the x-axis.
Okay.
That's the way to think about it. It's not a flattening by 3/4 because that would be quite a flattening. It's not as much as a double even. It's more like a flattening by a fourth because you're only losing 1/4. In other words, this point right here is only 1/4 closer to the x-axis. It's not 3/4 closer.
Okay. So, sorry.
That's all right. Go ahead.
So, like, what would a table look like for this graph?
Tables. Since we're dealing with quadratics, let's deal with both positive and negative numbers.
Okay.
So let's start with -2. Well, what is y when x is -2?
Let's see. So it would be 4, and 3/4 of 4 would be 3.
-3.
Or -3. My bad.
Okay. How about x of -1?
Let's see. That's 1 times 3. That's negative 3/4.
0.
Oh, 0.
1.
Would be negative 3/4.
Now it'd be positive.
Oh, would be positive?
No, my bad. My really bad. I'm really going to confuse you if I do that. Yeah, it's the same as when it was -1. Because this thing is symmetrical about the y-axis. So whatever -1 is, that positive one's got to give you the same answer. So 2 also has to be equal to -3. Okay? So there's a table, and that table kind of reflects here. There's the 0, 0 point. When x is -1, right there is -3/4. When x is -2, out here, well, the y value is all the way down to -3. Maybe not the scale I've drawn it, but the numbers are what's important. Of course, when x is +1, y is -3/4, and when x is +2, y is -3.
Okay.
So to make a table, that's all you do, is you just make up integer values for x and figure out what y is. And then, if you didn't know how to graph it, you could always graph it from the table. In other words, that's a surefire proof of graphing, is make a table, make your dots, connect the dots.
Okay.
But it depends on what they're trying to teach you here. My sense is that they're trying to teach you about translations of parent functions.
Yes.
As opposed to how to graph any function by making a table. In other words, they want you to know how to graph this based on your knowledge of what x squared looks like.
Right.
Okay. I'll leave that. Oops. You got another one?
Yes. H of x equals negative 6x squared.
Okay. What's the first thing we want to do if this is our standard?
Well, aren't we going to flip it?
Yep. Okay, so it's a flip first, and then what?
Isn't it a stretch?
Yes. So it makes it
Okay.
skinnier by a factor of 6. So it really
Okay.
makes it skinnier. Bigger that number is, the skinnier this would be. And you can see why. Whatever point is there is now 6 times further away from the x-axis, way down here.
Okay.
And if I found a point there, that's 6 times further away. Now if I connect my new set of dots, I end up with this skinny parabola.
Okay.
And the table, we can do a table. When x is minus 2, what is h of x?
Let's see. Okay. 2 times 2 is, that's 4. Maybe that'd be negative 24.
Okay, when x is minus 1,
Negative 6.
0, and then you can just, you don't even have to do the math for the others. That's going to
Okay.
be negative 6, and that's going to be minus 24 also.
Okay.
As long as the vertex is on the y-axis, that's true. If you start talking about parabolas that are shifted left or right, then obviously that's not going to be true. In other words, if I have a parabola that is like that, well then an x of plus 2 is not going to give you the same y value as an x of minus 2. Because this thing is symmetrical about that line right there. Okay? And how would you get a parabola like this? By having an h of x of, say, something like x minus 1 squared. This minus 1 means we're going to move 1 unit to the right. So my vertex would be right there at 1.
Okay.
Okay? And it's always x minus h. Is the way I kind of like to think about this. Is the standard is x minus h. So when I'm looking at x minus 1, it means h is a positive 1. Positive means shifted to the right. Negative means shifted to the left. So if I had an x plus 1 squared, that would be shifted 1 unit to the left. Same shape. Does not change the shape when you do a horizontal shift. Not a squeeze or a stretch, which both change the shape of the curve. When you're doing a horizontal or a vertical shift, it's merely moving it up or down or left or right without changing the shape at all. And you get that, you get the horizontal when the number is inside the parentheses. In other words, when I've written it like that, what I'm really talking about is f of x plus 1. When I say the number is inside the parentheses, I mean those parentheses.
Okay.
Now maybe you haven't learned all 6 of these things yet.
No, we haven't really gone the depth about like the h of x equals x plus
It looks like
squared.
right now the only thing you're dealing with are reflections and vertical stretches or squeezes.
Right.
But you'll get to the others. You'll get to the horizontal shifts and the vertical shifts at some point.
Yeah, we're also doing different equations for these two.
Okay.
So I think we have like vertex, intercept, and I forget the last one.
Okay.
It's like
So what's the last function?
The next one.
Uh-huh.
Okay. The next one is g of x equals x squared plus 5.
Okay, now this is different.
Mhm.
This is a vertical shift. In other words, what this is f of x plus 5.
Okay.
If I said, what is f of x plus 5, you'd say x squared plus 5, right?
Right.
Well, notice this plus 5 comes after the function. In other words, if you look at it in terms of that,
Mhm.
the vertical shifts are when you have a number that comes after the function. It's up if it's plus, it's down if it's minus. So if I want to plot g of x, I merely take my regular parabola, move it up 5 units. The vertex is no longer at 0, 0. It's at 0, 5.
Okay, so simply just goes up by 5.
And it does not change shape. There's no squeezing, there's no stretching. It's called a vertical shift.
So what would a table look like for that?
Same thing. In other words, the tables are easy.
Okay.
I'll leave the left part of that table. You tell me what g of x is. When x is minus 2.
Okay, so let's see, that'll be 4 plus 5.
9.
Right?
When x is
9.
minus
Okay.
1.
Okay. Okay, so that'll be just 6, right?
When x is 0.
0. Or sorry, my bad, 5.
All right. When x is 1.
6.
And when x is 2.
9.
Now, those are the same because we're still centered on the y-axis. We're not at the origin anymore, but it's all we've done is moved it up or down.
So if the vertex were to change left or right with the graph,
then these numbers are not going to be the same for positives and negatives.
and wouldn't you center the graph around the vertex?
Yeah, you always have a line of symmetry that goes through your vertex. In this case, the line of symmetry is x equals 0. It's a vertical line that is the y-axis, which is defined by x equals 0. But you're right. If I had a parabola out here, then the values are not, they're all going to be symmetrical about the vertex, but minus 2 is not going to give you the same value as plus 2.
Okay.
This kind of table you get only if you're centered about the y-axis. Then you get all the positive numbers are the same as the negative numbers.
Okay.
Okay.
Okay, the next one is negative x squared, or sorry, h of x equals negative x squared minus 4.
Like that?
Yep.
Okay. Because parentheses will make a great deal of difference here.
Okay.
Okay. So we got two things only going on. What are they?
Let's see. It's going to be would that be a horizontal flip?
Yes, a reflection over the x-axis.
Okay. Sorry, my bad.
It's all right. That's a horizontal flip. I mean, you could call it that.
Okay.
If that's the way your teacher talks about it, then that's what I should say. But either one mean the same thing.
Okay.
And
So
then what? What's the consequences of the minus 4?
wouldn't that be a vertical stretch?
No? Remember what we're talking about here is f of x minus 4. That's a vertical shift.
Oh, okay, my bad.
Down by 4 units. Okay? But first of all, we got to reflect it.
Okay.
In this case, it doesn't matter which you do first, but there are plenty of cases where it will matter. So there's the reflection, Now we move this reflected curve down 4 units so that the final curve looks like this. Okay?
Okay.
Now, notice that if I were to move it down 4 first and then reflect, it doesn't look the same. Watch what happens.
Okay.
I'll draw it in blue.
Okay.
I'm going to move it down 4 units first. And now I'm going to reflect that.
Oh, okay.
So the order you do these is very important.
So when you flip, you don't flip on the vertex, you flip directly on the x-axis.
Exactly. You're not flipping about the vertex, you're flipping about the x-axis.
So when you're describing the transformations, you have to do the reflection first.
Yes.
Okay.
Always. And in this particular situation where you have a vertical shift and a reflection about the x-axis, it does matter which you do first. If it was a horizontal shift instead of a vertical shift, it's not going to matter which you do first. But rather than trying to keep that all memorized, just always do your reflections first. And then there'll never be any problem. Okay?
So, yeah, what would the table look
Okay?
like?
When x is minus 2, what do we have?
Let's see. That'd be 4 minus 4, right?
Don't?
Or no, we make it a negative. So that'd be a negative 4. That'd be a negative 8.
Yep. When x is minus 1.
See, that's negative 5.
X is 0.
Let's see, that'd be minus 4.
And we know these values are going to be the same because we're still, our line of symmetry is still the y-axis. So this has to be minus 5 and that has to be minus 8.
Okay.
Okay?
Okay, the next one. Oh, sorry. Okay, the next one is n of x equals 1/3 x squared minus 5.
Like this?
Yep.
As opposed to,
Yeah, no, nope, it was the first one.
right. This one is a horizontal shift.
Okay.
Okay, that's the difference. If I have it parentheses around the x and I have a number in there being added or subtracted, it's going to move that parabola left or right. So that's why I asked about the parentheses, because it really matters a lot.
Okay.
In this, we only have 2 things going on. What are they?
Let's see. Oh yeah, it's going to be a vertical shrink, or yeah, shrink.
Yep.
A factor of 1/3, and then it's going to move down 5 points.
Right. There's no reflection, so it doesn't matter the order you do it. If there's no reflections, you can do them in any order you want. So I can move it down 5 units and then make it skinnier by a factor of 5. Oh, excuse me, what am I talking about? Wow. It's getting late. I had a lot of sessions today. Yeah. I can move it down by 5. Let's do it in 2 steps. And then make it flatter by a factor of 1/3. I'm not even sure if that's the correct terminology. Make it flatter maybe by a factor of 3. I don't know. I don't think the terminology matters as much as you know. Is all that means is that
What, you mean factor of 5?
No, we're talking about the 1/3 makes it flatter.
Oh, okay.
5 merely moves it down 5 units.
So by a factor of 1/3.
Yeah. In other words, yeah, we're 1/3 closer to the x-axis than we are on the other curve.
Okay.
Whether you want to call that a factor of 3 or a factor of 1/3, I don't know. But
Okay.
and the table, again, is relatively easy. And we're still centered on the y-axis. So these two numbers will be the same as those two numbers. So let's just do -2.
Okay. Okay, so that'll be 1/3 of 4, right?
So that's 4/3
4/3.
minus 5. 4/3 minus 5, which is 15/3, gives you -11/3. So
Okay.
minus 11/3. And then when x is -1, what do we have?
Okay, -1. That's so 1/3 of 1. Just be.
So that would be 1/3 minus 15/3 or minus 14/3.
Okay.
When x is 0, what's h of x or n of x?
That's -5.
And then these numbers are the same, minus 14/3, minus 11/3.
Okay.
Okay?
Okay. The next one. You're just giving me 1 second here. Okay. The next one is f of x equals -3x squared plus 3x minus 4.
Okay. Now we have a quadratic whose vertex is not on the y-axis anymore.
Okay.
There are two methods of graphing this. I don't know exactly how to graph that when I'm looking at it like that. I know that because there's a negative in front of the x squared, it's a parabola that goes like that. I know that much, but I don't know where it goes. I don't know whether it goes here or here. So the first thing I need to do is figure out the vertex.
Okay.
Have they taught you a formula for the x-coordinate of the vertex? Minus b over 2a?
Yep.
All right. That's one way to do it. Let's do it that way.
Okay.
First of all, that's A, that's B, that's C.
Okay.
So what does minus B over 2A become?
That would be -3x.
No, just the coefficient.
Okay.
Not the variable. Just the coefficient is B.
Okay.
What's 2A?
Excuse me. It would just be +9.
A is -3. 2 times A is -6.
Okay.
So
Sorry.
that's equal to 1/2, positive 1/2. And that is the x-coordinate of the vertex, or the new line of symmetry. In other words, if I draw a vertical line through the point 1/2, right there, that's what I'm going to be centered about. Now, I still don't know where my vertex is because I still don't know where the y-coordinate is. So how do you get the y-coordinate of the vertex?
I don't know.
Plug in the x-coordinate into the function.
Okay. So wherever you see x, you put in 1/2.
So let's see. That becomes minus 3 times 1/2 squared plus 3 times 1/2 minus 4. Well, what's 1/2 squared?
Let's see, 1/2 squared is half of a half is a fourth, right?
So that's minus 3/4 plus 3/2 minus 4. So let's see. If we put everything in fourths, we got minus 3/4 plus 6/4 minus 16/4. What is that? Minus 19 plus 6. It looks like minus 13/4. Minus 13/4 is the y-coordinate of the vertex. Well, minus 13/4 is minus 3 1/4. So if I go down here, right there is the vertex. Okay? And that's a huge point to find when you're trying to graph a parabola. That is the most important point. However, I need two other points. Parabolas are determined by 3 points. If you give me 3 points and tell me it's a parabola, that's all I need to draw it.
Okay.
Well, I got some choices as to how to get my other 2 points here. There's a ton of ways to do it. It kind of depends on what your teacher wants. If your teacher wants the x-intercepts, that's one way to do it. If your teacher merely wants 2 other points or maybe wants the y-intercept, that's actually an easier way to do it with this problem.
Just any.
There aren't any x-intercepts. Why? Because that's the vertex and I know that it points down. So it's got to go like that. Question is where does it cross that y-axis? Right there. Why? Because it crosses the y-axis whenever x is 0. Well, whenever you let x equal 0 in a quadratic, the only thing you're left with is the constant. In other words, if I plug in x of 0 into this thing, I get minus 4. So we're going to cross the y-axis at minus 4. Well, that means we have a point right there, because we know that it's symmetrical, that's also minus 4. Well, this y-axis was 1/2 unit to the left of my line of symmetry, so this is 1/2 unit to the right.
So it'll be 1.
Yeah, so that's 1 comma minus 4 is this point here. This point is 0 comma minus 4, and the vertex is 1/2 comma minus 13/4. So there's the 3 points that determine that parabola. And that definitely is the way to do this parabola, because this parabola doesn't have any x-intercepts. And they don't always have x-intercepts. A lot of times a parabola will go through the x-axis, and so you'll have 2 intercepts, and then that's what your teacher wants, is those 2 points and the vertex. But if you have a parabola that doesn't go through the x-axis, then like that, then the best points you can get are the vertex and the y-intercept. And once you get the y-intercept, you can figure out what this point is over here as your 3rd point, just based on symmetry.
Okay.
Now, there's another way to do this besides the minus b over 2a. And that is to put this quadratic into vertex format. Have they taught you that yet? Vertex format being a times x minus h squared plus k.
Yes, they have.
Okay. If we can get this into this format, then we know the vertex automatically. The vertex is h comma k.
Okay.
The difficulty is that it's relatively difficult to get this thing into this format. You have to complete the square.
Okay.
Let's do it just to show you. We got 15 minutes and might take that long to... Have they taught you completing the square?
They might have. I don't recall.
Well, I'll teach it to you anyway, because you'll learn it soon enough. Here's my function. I want it to look like that. Okay, here's how you do it. Let's erase the grid here. Because if I can get it to look like this, then I can graph it almost instantly. At least I know where the vertex is.
Okay.
It was fairly difficult to figure out where the vertex was. I had to go through two steps. I had to plug in minus b over 2a, and then I had to take that value and plug it in here to find out the y-coordinate. So figuring out what h and k are was relatively tough doing it this way. But if I want to put this into this format, well, I have to complete the square, and the way you complete the square is by separating the x's and putting the number off to the side. I'm putting parentheses around the x's. So that's the first thing I'm going to do is put that minus 4 off to the side. Okay?
Okay.
Now, in order to complete the square, I have to get the coefficient of the x squared term to be 1. Always. Not, right now it's minus 3. So let's change this. Factor out a minus 3, leaving behind x squared minus 1.
Okay.
Right? Hold on. Excuse me. X squared minus x.
Okay.
And I leave room. Put my parentheses over there. I still have this minus 4. Now, have I changed the function, or do I still have what I started with?
You changed the function.
No, I haven't, really.
Well, no, because sorry, my bad, because it's factored.
Right. In other words, if I multiply this back together again, I got exactly this. And that's the key thing. You always want to make sure you never change the function. Okay?
Okay.
So now I can complete the square inside the parentheses. Completing the square is relatively easy. You take the coefficient of the x term, which is 1, or minus 1. You divide it in half, square it, and add it. Well, 1/2 squared is 1/4. So I'm going to write a 1/4 in there. Now I've changed the equation. How much did I just add or subtract to this function?
1/4.
Times minus 3.
Oh,
So I really subtracted 3/4, which means I have to add 3/4 to balance it out. Now, if you examine this function with this function, they're the same thing.
okay.
If you distribute this to that and you add those two numbers, you'll get this. In other words, again, I have not changed anything. Because when I wrote in that 1/4, is all I had to do was balance it on the same side of the equation by doing the opposite. Well, I really subtracted 3/4 when I wrote in that 1/4, so I have to add 3/4. Well, now, the reason you complete the square is so that I can write this as an x minus h squared. Notice what I now have. I now have minus 3, and the part that's in the parentheses I can now write as x minus 1/2 squared. Add those two numbers together, you get 3 1/4. Now I've got it in perfect vertex format. Notice what the vertex is, hk. There's h. Remember it was 1/2?
And then
and it was
negative 3.
minus 3 and a quarter.
Okay.
So once you have converted your function to vertex format, you don't have to go through all that nonsense of minus b over 2a. You know exactly where the vertex is. You also
Okay.
know that it's reflected about the x-axis, it's stretched by a factor of 3, and it's vertically shifted down by 3 1/4. So I know a lot about this function, but I could also find two other points relatively easy. There's a number of ways to do it. So what technique you use to graph a parabola or a quadratic, you got a lot of choices. You can use the minus b over 2a technique and go through that process. You saw how difficult or easy that was. Or you can use this technique. Personally, I favor this only because I've done a lot of completing the square, so I'm used to doing it. A lot of students probably find completing the square a more difficult task than the other method. But the thing about completing the square is that you have to do that with a lot of other kinds of math also, not just graphing quadratics. When you get to conic sections, you're going to have to complete the square. When you get into calculus, you're going to have to complete the square. So completing the square is a mathematical tool that you want to get good at and know how to do it. They may not have actually taught it to you yet. I may be getting a little ahead of things here. The only thing they may have taught you is the minus b over 2a and then how to get the y coordinate also. But we complete the square in order to be able to write it like that. I want it to be x plus or minus some number quantity squared. And if I can do that, then I've written it in that format. And this format is easier to graph than this format, at least immediately. It's certainly easier to find the vertex. The vertex is staring at us in the face. It's 1/2 and minus 3 1/4. And once you know the vertex, putting the other 2 points on there is actually relatively easy. I know the y-intercept is minus 4, for one thing. So if I've put this thing into vertex format, well, now I know where the vertex is, I know where the y-intercept is, I can figure out that third point real easily, and I'm done. So to me, putting it into vertex format is a little easier than doing the other method. But for you, maybe not, especially if they haven't taught you this method yet. Got another one? We got 5 minutes.
Okay. Do you think we can do a word problem?
Yeah.
Okay. It says the balance, y, in dollars, of your savings account after T years is represented by y equals 200 times 1 plus 1 t. Oh, 1.1 t. Yep.
That means you're earning 10% annual. Because the real equation is this. Y equals your starting amount. We'll call that y sub 1. We'll call it a sub 1. The amount you started with. Times 1 plus the rate of interest to the t power. There's the general equation for compounding annually. So in your case, you started with $200. The interest rate is 10%, which converts to 0.1. Add 0.1 to 1, and you get 1.1 to the t power. So there is the specific equation for our problem. So plug in whatever t you want, and you find out how much your balance is worth after that many years. In other words, at the end of 1 year, it's worth $220. At the end of 2 years, you plug in 2 for that and figure out what you're looking at. So in other words, you might need a calculator to come up with these numbers depending on what t is. So the question specifically said what? What's your balance after?
It said the beginning of your balance of your friend's account is $250, and the balance increases by $20 a year. It says write a function which represents your friend's account.
Okay. And the friend's account started at $250?
And increases by $20 each year.
Okay. I don't like that because it doesn't really. Increases by $20 the first year because you make 8%. So if it increases by $20 the first year, then you've made 20 divided by 250 or 0.08 or 8%. So the equation would be y equals 250 times 1.08 to the t power. In other words, you're not making $20 per year in interest, you're making 8% per year. And the reason that it makes a difference is because in year 2 you make more than 20. Notice that at the end of year 1 you got $270 now. Well, when you make 8% on $270, that's more than $20.
Okay.
So they didn't word the problem quite right. If they said that he started with $250 and he made $20 the first year, then it's worded properly. Because then you can come up with what his interest rate is, which is 8%, and then you can come up with this exact formula. Because remember, inside the parentheses is 1 plus the interest rate. And the interest rate is usually fixed. In other words, if you go to a bank and they say they're paying 8% per year, that's what they pay. They don't tell you we're going to give you $20 a year. They may say that your 8% the first year is going to earn you $20, but the second year it'll earn you more than $20 because at the beginning of year 2 you don't have $250 anymore, you have $270. So when you make 8% on $270, it's more than 20. It's like 23. It's like 22. But that's why you end up with an exponential equation over here instead of an algebraic one. And the difference is exponential equations have the variable in an exponent. Algebraic equations have the variable on the equation line.
Okay.
Exponential equations are harder to solve. We don't really have algebraic ways of solving them. We get into logs and stuff like that when we go to solve equations like this. I mean, it's easy enough to substitute a number for t. If I want to know how much money I have after 2 years, I put 2 there. And then I put this into my calculator, 1.08 squared times 250. That's how much you'd have at the end of 2 years. I want to know how much I'd have at the end of 10 years. I stick a 10 there. And I take 1.08 and take it to the 10th power and then multiply that by 250.
Which would be, would that be 108?
No. Do you have a calculator in front of you?
I
got one right here. Hold on.
Okay.
Do you use the TI-84?
No.
Don't use this one here?
Yeah, no. That's really cool.
1.08 raised to the 10th power is going to be a big number. Well, not that big, 2.15, which means in this case more than double. In other words, at 8% per year, you more than double your starting amount. It's times 2.15. So your $250 would turn into 500 and change.
$500?
More than 500. 500 and change if you left it in there for 10 years. And you earned exactly 8% every year. Okay? So that's the general way to do these compounding interest problems. And this actually can get quite complicated. It makes a difference whether you're compounding yearly, compounding quarterly, compounding continuously. You have 3 different general equations for each type. And they'll teach you that also, but they're starting off with this.
Okay.
Okay? All right, Connor, I will let you go, and hope that's been helpful.
Yes, thank you very much.
All right, talk to you next time.
Okay, bye-bye.